All right, hello everyone. We're in section 5.4. We've now done sampling distributions of a mean. Now we're going to do sampling distribution of a proportion. So in class, we should have done a little simulation. I hope we did that. That simulation was simulating, instead of grabbing a bunch of people and asking for their area of the rectangle or some number question where we could find the mean. Now we're just going to basically ask them a yes/no question. This is called sampling distributions of a proportion. Sampling distribution of a proportion. So in other words, we just ask a question. It's like a yes or no, success or fail. We often call it success and fail. Those are loose terms because we don't know what success or fail is. The example I think we did in class was a seatbelt. We knew that 60% of the population wore a seatbelt. So what happens with our samples? So what we want to do is the same basic thing we did for the mean, is figure out what the mean and standard deviation would be for the sampling distribution so we can answer questions. So before we do that, we have to do a little bit of work. So P is probability of success. I probably already mentioned that in the simulation. Q is the probability of failure. So I use P and Q. What we want to do to find the mean, and this mean is a looser term because it's just the average. It's not like the mean based on like the average of a bunch of areas. It's what we expect to happen in essence. So 40% is our no's. So we're putting our no's, giving them a 0. What we're going to do is put a numerical value to yes or no. So no's are 0, yes or 0. We're just counting up how many yeses we got. Based on this information, if our population has 40% no's and 60% yeses, if we took a sample of 1,000, we would expect around 60% yeses. Okay, so what we want to do is look at how to find the average and the standard deviation based on these numbers. So I'm going to kind of go step by step here. Actually, let me cover this up so not to confuse the issue. So the mean, we've done distributions before. We could put this in our calculator, by the way, and just figure it out. But we want to use a formula. So we could just dump 0, 1 as list 1, 0.4, 0.6 as list 2, find the standard deviation. But I'm going to remind you of those formulas because we're going to do them with P's and Q's in general, so we don't have to do it every time. So the first step to find the mean is just 0 times 0.4 plus 1 times 0.6. Okay, that's that math. We've done that before. Again, your calculator could do this for us. And we get 0.6, which happens to be P, which is what we'd expect, right? We'd expect whatever the probability of my population is to get the same answer, roughly the same answer when I take a sample. Now, to find the standard deviation, we have to take each one of those data points and subtract the mean, square it, multiply it by how many times it happens. Hopefully you remember this formula. Again, you could just dump this into the calculator. I'm going to give you a formula with P's and Q's at the end, so if you don't understand what's going on, it's probably not the end of the world. But notice 0, the data point, minus the mean, 0.6 squared times 0.4, how many times it happens. And then the same thing, 1 minus 0.6 squared times 0.6. We just do some algebra here. That's 0.6 squared times 0.4 and 0.4 squared times 0.6. Which then, if you factor out a 0.6 and a 0.4, there's 2 0.6s in the first term and 2 0.4s in the second term. Factor out the 0.6 and the 0.4, we get 0.6 plus 0.4, which is a 1. So you just get 0.6 square root of 0.6 times 0.4. This is going to happen every time. I'm going to show you with P's and Q's. We're going to do it really fast. But it turns out then that the mean, oh gosh, sorry about that. The mean is P. The mean is P, and the standard deviation is the square root of PQ. Okay, so I'm going to just show you in general the PQs. I'm not going to spend a ton of time on this. You can pause the video if you want. I just did the same exact math with P's and Q's instead of 0.6s and 0.4s. Okay, so that's what you see there. 0 times Q, 1 times P. I'm just going to kind of move along right now. You can pause this and just look at that if you want, but that kind of proves that we can do it with P's and Q's instead of 0.6s and 0.4s every time. All right, so let's put this together now as an example. It's going to feel a lot like the last section. So here's the basic idea. is we know that in a population, 60% of all drivers wear a seatbelt. All right. Oh, sorry. This is the same example. So this is putting it all together. Oh, sorry. I kind of spaced out there for a second. So just kind of forget about that. We don't need this. We're going to do a problem in just a second. So just as a notation, P hat. I don't know if I mentioned this in class or not, so I'll just say it again. P hat is P is the proportion of successes in your population. P hat is the proportion of successes in your sample. Okay, so P hat by definition is just the number of successes over the sample size in your sample. Okay, and then like I said, P is the proportion of successes in your population. We're just going to put it all together. All this is basically is what I just showed you. So I can do some example problems. Here are the properties of the sampling distribution of sample proportion. The first property is that the mean of the sampling distribution, mean P hat, equals the mean of the population, or sometimes we just say P hat equals P. Second part is the standard error, or standard deviation of the sampling distribution. We're going to get this the same exact way we got the mean, believe it or not. Remember, we took the mean standard deviation and divided it by the square root of the sample size. We're going to do the same thing here. But just remember that the standard deviation is square root of PQ, right? So it's like the square root of PQ. That's, remember in the mean, it was this. Now it's just this. It's the same basic formula, except the standard deviation comes from a different place, right? Remember, in the mean problems, we tell you the population standard deviation. Here, we're just going to tell you the proportion of successes, and you have to figure out the standard deviation by yourself. So this is square root of PQ over N. And then maybe most importantly is, is it going to work? We need a big enough sample size to make this roughly normal, because I'm about to use the normal curve to answer some questions. So the normal curve has to work. And in order for the normal curve to work, we need a big enough sample size. Back in the mean, it was 30. But this is a different problem, and this is totally dependent on P and Q now. So it turns out that if N times P and N times Q are both greater than or equal to 10, then we're okay. We need that restriction to hold true. We need to have that happen in order for the sampling distributions to be roughly normal, because I'm going to answer some questions about it, like I will show you right here. Let me do a little example. It's the same thing. So now in the 2000 census, 53% of the population over 30 were women. 9 of the 100 senators were women. Is this reasonably likely? Is it in the middle 95%? If it's totally random, the idea is that gender plays no role. Okay, it's the same sort of question. I'll probably answer just one of the questions. Like if I have a population, 60% wear seat belts, randomly select 40. What's the chance of having greater than 75, less than 25? It's all the same basic questions, right? So let's go back to this first one here. We're going to come down here. And then we'll do a seatbelt one next. Okay, so here's the general idea. It's very simple. It's going to feel a lot like the old problem. We're going to draw a little normal curve. And we got 53% of the population were over 30. So that's my P, right? My P is 53%. I'm going to sample 100. I'm going to sample 100. My mean is going to be 0.53. Remember the mean of the sampling distribution. So this is the sampling distribution. Is 53%. The standard deviation is going to be 0.53 times 0.47 square root of PQ over, let me just put it all over N, and the sample size, which in this case is 100. And then the question is 9 reasonably likely, or 9%, I guess is a better way to look at that. Is it reasonably likely? So we're going to have these little cutoffs here that are the reasonably likely cutoffs. Okay, so there's lots of questions I could ask. I could say, what's the probability that we get more than 50%? It's just a normal CDF problem. We're going to do one of those in a second with the seatbelt. For this case, we would want to find these cutoffs, right? We want to find these cutoffs. So remember, this is going to be an inverse norm on our calculator. We want those cutoffs, so we're going to go 0.025, because that's this area right here, 2.5%, with a mean of 0.53 and a standard deviation of 0.53 times 0.47 over 100. And we take out my little calculator and we go inverse norm, 0.025 with a mean of 0.53 and a standard deviation of the square root of 0.53 times 0.47 divided by 100. And I get 0.43, which you probably would have realized 9% is pretty unlikely, right? And by the way, I can just use a little symmetry, 0.63 on the other side. We just go 10 on the other side. So clearly, it's not reasonably likely. It's in that range. That would be a rare event. Could happen. And by the way, we could figure out the probability. We just go normal CDF. This is the other way to do it, right? If you don't want to find those cutoffs, if you want to know if it's reasonably likely, just do the normal CDF from negative infinity to 0.09% with a mean of 0.53. And we just figure out that, we just figure out that probability, square root of 0.3. It's going to be really, really tiny, right? Less than 2.5% is the whole idea, right? It's going to be super tiny, probably going to be 0 on my calculator because it's going to be so small. So negative infinity to 0.09 with a mean of 0.53 and a standard deviation of 0.53 times 0.47 divided by 100. Yeah, and I get basically 0, which it's so far away we can kind of do that. All right, so let's do it with a seatbelt problem. So number 2 here. I'm going to scroll down and rewrite it again, but we got 60% of the people wear seatbelts. We're going to randomly select 40. What's the chance that 75% or more? Would it be unusual to have less than 25%? And then we're actually going to change to, instead of proportions, we're going to change to numbers, just like we did with the mean. You can always do totals instead of numbers, so I'll come back to that in just a second. Actually, I'll just squeeze it in right here. So again, remember my population was 60. We're going to take a sample size of 40. And the question is, what's the probability that we get more than 75%? And then the other one is, would it be unusual to have less than 25%? So I'm going to draw a little curve. By the way, I should make sure I can draw that curve. Remember, NP and NQ both have to be greater than or equal to 10. So 40 times 0.6 is 24, and 40 times 0.4 is 16. So we're bigger than 10. So I'm allowed to, otherwise I can't draw this normal curve. And anytime I hit that normal CDF button, if it's not normal, it doesn't make any sense. Remember, the mean is going to be 0.6. The standard deviation is going to be 0.6 times 0.4 divided by the sample size. And I have 2 different questions. I'll just do one each. The first one is, what's the probability of greater than 75%? So that becomes normal CDF from 0.75 to infinity with a mean of 0.6 and a standard deviation of 0.6 times 0.4 over 40. I'll do that real quick on my calculator. 0.75 to infinity with a mean of 0.6 and a standard deviation of square root of 0.6 times 0.4 divided by 40. 2.6%. And then the next question is, would it be unusual to get less than 25%? So there's 25%. So same thing. We just go normal CDF from negative infinity this time to negative 0.25. No, not negative. Sorry, positive 0.25 with a mean of 0.6 and a standard deviation of 0.6. Times 0.4 over 40. We do that math. Negative infinity to 0.25 with a mean of 0.6 and the same standard deviation as the last problem. And I get, again, like super, super small, 0.00003, I think. Super small, less than 2.5%. That's the important cutoff for unusual, right? The question was, would it be unusual? And yes. Because it's less than 2.5%. Remember, it's outside the middle 95%. It's called a rare event. All right, and then the last question is this question. Same information, but instead of saying what's the probability that it's like less than 30% or less than 40% or whatever, we're going to ask a number of questions. So what's the probability that 30 or more wear seatbelts? So just like last chapter, last section, but I'm going to suggest you don't do this because we need to know this method for other problems. So I'm going to never do what I'm about to show you can do. You could just change that 30 to 30 out of 40 or 75%, right? So this is the same exact question as saying, what's the probability that over 75%? And then you just go through the same process. Or you just find a new mean and a new standard deviation. It works just like it did in the mean. Remember, the mean was the mean times the sample size, and then remember it was the square root standard deviation population times the square root of n instead of divided. Same thing here. Notice this is the same thing as this, right? So I'm going to scroll down. I'll do the same problem again. I'll scroll down here, and then we'll be done. Last problem. So remember, the question was, what's the probability that it's greater than 30 out of 40? So I'm not going to do average. I'm going to do total now. So now, since the average was 60%, right? Remember, I had 0.6 on there. If I had proportions, just so you can see both together, if I had proportions, this would be 0.6. But this needs to be 0.6 times 40, which is 24, yeah? We would expect on average, every time I do this, to get about 24 successes. Down here, my standard deviation would have been 0.6 times 0.4 divided by 40. Here, it's going to be 0.6 times 0.4 times 40. And now I want just over 30. By the way, over 75%. It's going to give me the same answer, by the way. You can do it if you don't believe me. Normal, up here, I'm going up here, normal CDF from 30 to infinity with a mean of 24 and a standard deviation of 0.6 times 0.4 times 40. Normal CDF, 30 to infinity with a mean of 24 and a standard deviation square root of 0.6 times 0.4 times 40, and I get 2.6%. There's a couple other examples in the book. If you need to see another one, we're going to do a lot of them in class tomorrow. I know sometimes only seeing one or two of these. That can be a little tricky, but just, I know I hate to say this, but you could probably watch the video again, kind of, if I went a little too fast, go through it a second time. The next section is going to be very, very similar, just a different summary statistic. This is really the same thing we just did. It's just a different summary statistic. So the formulas are a little different, but once you get the mean and the standard deviation, everything works exactly the same.